Hi everyone. Today we are going to be focusing on accumulation functions. And the good news here is that we actually did work with accumulation functions back in Unit 6. So now we're just going to be building on the work we did at that time. So just to refresh our memories, an accumulation function is just a function that is defined as the integral of another function. So in this case, this f of x, we would call, whoops, not I, our accumulation function because it's defined as the integral of g of t. Now, hopefully, if you remember back, a big part of working with accumulation functions was being able to take the derivative of these functions, and that really relied on us using the fundamental theorem of calculus. So just as a quick review, here's how that worked. We have a function f of x, that's our accumulation function, and it's defined as the integral of g of t. If I wanted to take the derivative of f of x, really what I would be doing is taking the derivative with respect to x of this integral. Now, if you remember back, the fundamental theorem said this. If we're taking the derivative of an integral, we know that derivatives and integrals are inverses of each other, so here's what happens. We're going to take that upper bound and plug it in for our variable. So instead of g of t, we're going to have g of x. And then fundamental theorem said, multiply by the derivative of that bound. So the derivative of x is just 1. Then what we did was we said we're going to subtract out. Now we're going to take our lower bound and plug it in for the variable. So I have g of 2, but now I also have to multiply by the derivative of that bound, but the derivative of 2 is just 0. So what happens is this whole term is 0, and we're left with g of x. So the derivative of that accumulation function is just equal to g of x. Now, our second one's a little bit different. My goal here is still to find the derivative. So I'm taking the derivative with respect to x of my integral. So now I'm still going to follow the same process. I'm going to plug in 4x for my variable. So I have g of 4x. But now the derivative of my bound here is going to be 4, so I'm going to multiply by 4. In this case, I could plug in 2, but remember I would still be multiplying by the derivative of 2, which is 0. So in this case, our derivative is just equal to 4 times g of 4x. And then the last case we have here is where I have two terms in my accumulation function. So I've got this 6x and I've got my integral. So if I want to take the derivative, I have to remember to take the derivative of both of these terms. Now the derivative of 6x is just 6. And then we previously saw the derivative of my integral is just going to be g of x. So the big thing here is to make sure that when you're taking the derivative, you keep in mind that you need the derivative of both terms. All right, so now what we're going to do is go over some vocabulary about graphs, and this is really a review of that problem that we did in class. So this is not new vocabulary, we're just going to be applying it to these accumulation functions. So remember, a critical point is where f prime, if I had a function, is equal to 0 or it does not exist. If I'm looking at the graph of f prime of x, I'll know I have critical points. Those are going to occur at the x-intercepts. For increasing, that's where our first derivative is greater than or equal to 0. And then again, if I have a graph of f prime, I'm looking for where the f prime of x is above the x-axis. That's how I'll know where I'm increasing. For decreasing then, it's where my derivative is less than or equal to 0. It's where the graph of f prime of x is below the x-axis. All right, points of inflection. This is where our second derivative, I'm going to say, is equal to 0 or doesn't exist. But here's where we said and, it's where f double prime changes sign. So we're not just looking for where it's equal to 0 or does not exist, but we have to show that it also changes sign. So in terms of the graph of f prime, here we're looking for where the slope of f prime changes sign. So from a positive to a negative slope or from a negative to a positive. Concave up is where my second derivative is greater than 0. If I'm looking at the graph of f prime, it's going to be where the slope of f prime is positive. For concave down, my second derivative is less than 0, and this is where the slope of f prime is negative. All right, so then for a relative maximum, here we're looking for where f prime of x changes sign from positive to negative. Okay, now on a graph of f prime, this is going to correspond to where the graph changes from being above the x-axis to below. So now the opposite is going to be true for my relative minimum. Here I'm looking for where f prime changes sign from negative to positive. And in terms of the graph, it's where it changes from being below to above the x-axis. All right, and almost done. Now for absolute extrema, here we have to find out basically our critical points. So where is f prime of x equal to 0? But we also want to consider where it's equal to 0 and where it changes sign. And this was where, if you remember back when we were doing absolute extrema, probably in Unit 5, this is where we made a table of values. So we actually would make a table for our x values and our function values and compare. And remember, in our table, we included our critical points and the endpoints. So all this vocabulary is stuff we have learned before. Again, we're just going to be applying it now to these accumulation functions. So what we're going to do through the rest of the video is go ahead and look at some sample problems. All right, so here we go. All right, we have here f is our function. It's defined on the closed interval from 0 to 7. We have a graph of f here, and it's defined, we have g, which is a function that's defined as the integral from 2 to x of f of t dt. So again, what we have here is g of x here is an accumulation function. It's defined as the integral of f. All right, so the first three questions are questions we had in the Unit 6 test. Those are not new at all. So if you remember, if I want to find g of 3, my function is defined here, g of x. So instead of x, I'm going to substitute a 3. So that means this is the integral from 2 to 3 of f of t dt. Now remember, when we have an integral here and we have a graph, this integral just represents an area. So it's the area between x equals 2 and x equals 3. So this shaded area here. And so that, we've got a trapezoid. So we have to remember trapezoid is h over 2. My height is just 1. So 1/2 times base 1, right here is 4. Plus my base 2 right here is 2. So I get 6 over 2 is 3. So that was just using my accumulation function. Now in the next one, they're asking for g prime of 3. So before I find g prime of 3, I have to figure out what g prime of x is. Well, g prime of x is just the derivative of this accumulation function. And we've seen this a couple times already. The derivative of that accumulation function is just f of x, which means that g prime of 3 is just equal to f of 3. Since this is the graph of f of 3 would just be the corresponding y value when x is 3. So that's just going to be equal to 2. All right, then the last thing, we've got g double prime of 3. So again, before I jump into 3, I have g double prime of x. Well, let's see. If g prime of x was equal to f of x, that means g double prime of x is just f prime of x. So I have g double prime of 3 equals f prime of 3. That derivative tells me I'm just looking for the slope when x equals 3. Now at x is 3, since I have a linear segment here, it's easy to find the slope using rise over run. So I can see I go down 2 over 1. That value is going to be negative 2. So parts A through C are just a review of where the work we've already done with accumulation functions. So here's where we get into some of the new material. So now it says to identify where g of x is increasing and decreasing and justify your answers. So let's take a look here. So we said that a function is increasing in general. A function is increasing whenever its derivative, well, its derivative, g prime of x, is equal to f of x. So where that derivative is greater than or equal to 0. And it's going to be decreasing. Again, I'm looking for g, so where the derivative of g, which is just f of x, is less than or equal to 0. And again, this corresponds to now f of x being greater than or equal to 0. I'm looking for where that's above the x-axis. And it's decreasing wherever it's below. So we would say g of x, I'm going to scooch this up, sorry if it's crooked here. G of x is increasing, let's see, where that is increasing, where it's above the x-axis, is going to be from 0 to 4, and then from 6 to 7. That's where I'm above the x-axis. So increasing on the interval from 0 to 4, and 6 to 7, because now I'm going to say g prime of x, which is equal to f of x, is greater than or equal to 0. So now I've made the connection to g, but I've also made the connection to the graph here of f. So now g of x is decreasing. So again, that was where it's below the x-axis. It's decreasing on the interval from 4 to 6 because g prime of x, which is equal to f of x, is less than or equal to 0. Now, notice in my justifications, I did not say because the graph is below the x-axis or above the x-axis. I used the definition for increasing and decreasing in my justification. All right, next one asks for the x-coordinates of the critical points. So remember here, the critical points are where, I'm going to draw a box around here. Critical points are where, let's see, I want the critical points of g. So it's where g prime of x equals f of x, where it's equal to 0. So all the values where that function is equal to 0. So let's see, let's tackle that first. So if I look I'm going to have critical points. F of x is equal to 0 when x is 0, when it's 4, and when it's 6. So all three of those would be my critical points. Now the question is, determine whether each of these points is a relative maximum, minimum, or neither. So for those things to happen, a relative max or a min, I need a sign change to happen. So let's look at x equals 0. Since that's one of my endpoints here, I don't have a sign change to consider. So we would say x equals 0 is neither a relative max nor a relative min because, again, I'm going to make a connection here between g and f. G prime of x equals f of x does not change signs at this value. All right, now let's see, x equals 4. Here I can see that my graph, f, changed from being above, so positive, to below, which is negative. When we change from positive to negative, that means we have a relative max. So we would say g has a relative max at x equals 4 because, again, g prime of x equals f of x changes from positive to negative at this value. Or you could say at x equals 4. And then lastly, we have to look at x equals 6. Here we see at x equals 6, my graph of f is changing from negative to positive, which means I have a relative minimum there. So sorry, this is going to be a little squished. We would say g has a relative min at x equals 6 because, oh boy, g prime of x equals f of x changes, in this case, from negative to positive at this value. All right, just a couple questions to go. We're going to be using the same accumulation function and the same graph. So if we flip over, next thing we're looking for is points of inflection. So we're looking for where our second derivative, in general, we're looking for where that second derivative changes signs, right? So at a point of inflection, I'd be looking for where g double prime of x, which in this case, we said g double prime of x equals f prime of x. We're looking for where that changes sign. Now, I also know that f prime of x is just the slope of f. So ultimately, I'm looking for where does the slope of f change signs. So I can look and see, well, I change from positive to negative at x equals 2. This is all negative, but then I change from negative to positive at x equals 5. So those are going to be my 2 points of inflection. So I would say g has points of inflection at x equals 2 and 5 because g double prime of x, which is equal to the f prime of x, and I like to make a note that says the slope, that means the slope of f. But g double prime, which is f prime of x, changes sign at these values. All right, what do we have? In part G, determine where g of x is concave up and concave down. So concave up, I know, is where g double prime of x, again in our case that's f prime of x, where is that greater than 0? And concave down is where g double prime of x, which is f prime of x, where is that less than 0? Now again, because this is slope, f prime, here I'm looking for a positive slope for concave up, and here I'm looking for a negative slope. So if I look at my graph, I can see I have a positive slope here, and here. So I would say g of x is concave up on the interval from 0 to 2, and then from 5 to 7, because g double prime of x equals f prime of x is greater than 0. Now for a negative slope, I'm going to have this interval here. Now, it's always a negative slope, but because I kind of have a corner-ish point here, I'm going to express this as two intervals. So I would say g of x is concave down on the interval from, let's see, 2 to 4 and 4 to 5, because g double prime of x equals f prime of x is less than 0. All right, almost done. The last thing asks us, to find the absolute maximum and the absolute minimum of g of x, and we're going to show our work. So here again, since I have absolute maxes and mins, here's where we need to make a table with our critical points and our endpoints. Now, when I'm thinking critical points, I'm only going to consider points where my graph changes sign, because I know I can only have an extreme value if my graph actually changes sign. So in my table, let's see, we'll have x and g of x. We're going to have our critical points where we change sign. So I'm going to include 4 and 6, but remember we also have to include our endpoints, so 0 and 7. So in my table, these are the 4 points that I have to test. Now, my function g of x is defined as the integral from 2 to x of f of t dt. So for each of these, I'm going to have an integral to calculate. So here I have from 2 to 0, f of t dt. Here I'm going to have from 2 to 4. This would be from 2 to 6. And I'm going to have from 2 to 7 of f of t dt. So now this is just an exercise in using areas to evaluate an integral. So from here, I notice here that my bounds are switched. This is really the opposite of the integral from 0 to 2, which is, let's see, look on your papers. I'm doing this as well because I don't think I could fit this. Well, let's see. Let me see if I can fit the graph in. There we go. So from 0 to 2, I have this triangle. So it's the opposite of 1/2. My base is 2, and my height is 4. So I get a -4 for that value. From 2 to 4, now this is, my bounds are in the right order. Again, I have a triangle. So it's 1/2. My base is 2 again. My height is still 4. So here I have a +4. From 2 to 6, let's see, I still have the integral from 2 to 4, so I've got 4. But now I have to subtract this rectangle. So it's 4 minus 1/2, my base is 2, and my height is 1. So I get 4 minus 1 gives me a value of 3. And for the last one, from 2 to 7, well, we're going to still have our integral from 2 to 6, which is 3. And then we're going to add in this rectangle. So plus 1/2 times base of 1 and height of 1 is 3.5. Now, this is the work. So now we just have to say g of x has an absolute max, let's see, that is going to be here, an absolute max of 4 at x equals 4, and g of x has an absolute min of, let's see, negative 4 at x equals 0. All right, so I know this is another long one. That's really all we need to cover for this. Again, most of the vocabulary is new. It's just managing kind of now these accumulation functions. So as always, please take good notes. Come to class ready with questions and ready to practice. Thanks, and I'll see you then.